Yes, let's go.
Awesome. I wrote a little introduction for you, actually, and for the people listening. So, welcome to the show. Today, I have a great pleasure and honor of introducing a truly remarkable guest, Professor William D. Phillips. He's an American physicist renowned for his groundbreaking work in the field of atomic physics, and he has been awarded the Nobel Prize in Physics in 1997 alongside Stephen Shu and Claude Cohen-Tanuji for the development of methods to cool and trap atoms with laser light. I think that's fascinating. We're going to talk more about that. And this pioneering research not only opened new frontiers for our understanding of creating new cool environments, but also paved the way for revolutionary advances in atomic clocks and quantum technologies. And so Professor Phillips is a distinguished scientist at the National Institute of Standards and Technology, the NIST, and a professor at the University of Maryland. He's also celebrated for his passion for science communication and education, inspiring countless students and audiences around the world. I had the joy of meeting him at the Lindo Nobel Laureate meetings in 2019, where before his lecture, everyone was promised a gift if they asked a question. And I was somebody who happened to sit in the first row, and I tried my best to ask one good question. And sure enough, I got a gift. It's actually this thing. Yep. And it's a
Yeah.
piece of memorabilia that has the current best measured values of the fundamental constants of physics and chemistry. And it is something I still have and cherish today because to me it represents the idea that our collective action can reach balance and consensus through the establishment of standards. So I'd like to thank you again for rewarding those who post questions. I think that's amazing. And with that said, I'd like to post questions to you, 5 questions today. And I'd like to thank you again for taking the time to answer these. I appreciate it. And with that said, I'd like to welcome you to the show, Professor D. William Phillips. Bill, welcome to the show.
Well, thank you very much. It's a pleasure to be here. Thank you for that very kind introduction. And I should say that we now have an updated version of that card with the best values of the fundamental constants. And I hope the next time that we see each other in person, I can give you an updated version of the wallet card of the fundamental constants.
Thank you so much. I really do appreciate your gestures, and I really keep them because it reminds me of good ideas.
And if you ever uh, need to do a back of the envelope calculation and you can't remember the value of, for example, Boltzmann's constant, well, it's right there on the card.
In fact, yes, yes. Perfect. Perfect for everyone. Yeah. So let's fire away with the first question. The first question is about research. Scientific research often starts with a vision, but almost always encounters unexpected turns along the way. These experiments can surprise us positively, deliver on our expectations, or fail to produce what we desire. But if things are right, they might just work. When conducting an experiment, how have you built clear expectations and accepted the uncertainty that comes with the territory?
Well, there's so many ways of answering that question. So let me tell you a particular story that relates to that question. When I was a uh, a newly minted PhD at MIT, just beginning to do a postdoc. My thesis advisor, Dan Klepner, who has just passed away a few weeks ago, and I'm still mourning his loss because even after all these years, he was someone to whom I would turn for wise advice in so many things. And he's someone who has had such a profound influence on um, on physics over his career that it's hard to overstate how important he has been. But anyway, in 1976, he came to me with a proposition. He had been inspired by a paper that he had read, which is so often the way things happen, to pursue Bose-Einstein condensation of an atomic gas. Uh, in 1924, Einstein, based on some new ideas that the Indian physicist Satyendra Bose had about the indistinguishability of photons, Einstein extended that idea to the indistinguishability of atoms and concluded that if you've got a gas of atoms cold enough and dense enough, if those atoms were bosons, what we now call bosons, at that time the, uh, the terminology didn't exist. Uh, if you had such atoms in a gas that was cold enough and dense enough, it would undergo a phase transition. And this would be for an ideal gas, which already is quite remarkable because phase transitions normally happen because gases are not ideal. That as you cool them down, the atoms start to stick together to form molecules and then form clusters and finally liquids, so that a phase transition from a gas to a liquid happens because the atoms interact with each other. So he described a phase transition in an ideal gas where there are no interactions. The phase transition is entirely due to the quantum statistics. And the nature of the phase transition is that a large fraction of the atoms stop moving, or at least that's the way he saw it. Today, because we understand about Heisenberg's uncertainty principle, we understand they're never going to absolutely stop moving. We would say they go to the lowest possible energy state. Well, anyway, that's the background. No one had ever seen this happen in a gas. There were hints that something like this was happening in liquid helium when you cooled it to its superfluid transition, but that was in liquid in a system that's very far from the ideal gas that Einstein imagined. So, so uh, Dan Kleppner comes to me with this idea and proposes to me that I begin to work on it, along with uh, uh, his colleague Tom Graytack, who worked in low temperature physics. Dan is an expert in atomic physics, and they wanted somebody to start working on this. Well, it sounded exciting to me, and we started working. Now you'll see in a moment why I chose this story to illustrate the the kind of idea that you suggested. We thought that atomic hydrogen would be the best atom to do this in because atomic hydrogen is uh, when you've got the electron spins of the atomic hydrogen all uh, uh, polarized, all aligned in the same direction, it cannot form molecules. So it seemed like a good approximation to an ideal gas. Um, and we thought, well, that's what Einstein did his calculation on an ideal gas. We want to do something as close as possible to what Einstein was suggesting, because the things that people proposed as examples of Bose condensation were very far from what Einstein had done, like liquid helium, or for that matter, uh, superconductivity was another example, uh, which seemed very far from the idea of an ideal gas. So, so we thought that hydrogen would be ideal, so to speak, as the thing to approach this. And I started working on it. I worked on it for 2 years, and then came to where I am now at NIST. And although I'm speaking to you from the University of Maryland, um, uh, we were so wrong that this was the right way to do things. It turns out that the way in which Bose-Einstein condensation was finally achieved involved what's called evaporative cooling. We thought back in 1976 that we would use conventional cooling. We would get the coldest refrigerators you could get, dilution refrigerators, uh, cool our sample down to millikelvins of temperature, and by what we might call conventional refrigeration. That is, you connect your sample to the mixing chamber of a dilution refrigerator, and if you're very careful, you may be able to cool it down to 10 millikelvin. And if we make the density high enough, then we should see Bose-Einstein condensation. That's not the way the community finally achieved Bose-Einstein condensation. What we did instead was use laser cooling, and then by holding the gas not in a conventional vessel, but in a magnetic trap, uh, basically a magnetic bottle that would act on the magnetic moment of the atoms. And hydrogen has a magnetic moment and works just fine in this regard. And then by allowing the most energetic of the atoms that have the most kinetic energy, by allowing those to escape, we could do what's called evaporative cooling. Now, this is just like what happens when you want to cool off your coffee. You blow on it, and that removes the saturated air that's above the coffee so that more water can evaporate. And every time a water molecule leaves the surface of the coffee, it takes away more than the average energy of the water molecules that are there. Well, this idea was the same thing to allow the most energetic ones to escape and leaving what's left behind at a lower energy. But here's the key point. The atoms that are left behind need to interact with each other and re-equilibrate so that you repopulate the highest energy part of the velocity distribution. If the atoms don't interact with each other, that won't happen, and the whole process won't work very well. Well, it turns out that hydrogen is not a very good gas for doing that. You don't have a lot of collisions that will re-equilibrate the sample. I mean, it works a little bit, and eventually, something like 22 years later, they finally achieved Bose-Einstein condensation, and this is after people had achieved it in gases like rubidium and sodium. So this first initial idea that we had was so wrong. That is, we thought what we wanted to do was to do Bose condensation in an ideal gas. And what we ended up, when I say we, I mean the community, uh, what we ended up doing was doing it in a gas where there were fairly frequent collisions, where there was a lot of interaction. The key thing, which we didn't understand at the time, was that we needed a good ratio between what we call good collisions and bad collisions. We weren't even thinking in those terms when we started. The good collisions are the ones that re-equilibrate the velocities. The bad collisions are the ones that flip the spins of the atoms, something that we didn't even understand how that would happen when we started. So, so when we started, we had made all kinds of assumptions that were wrong. And it turned out that the things that we started off with were just not the right way to do it. But here's the point that I want to make. Dan Kleppner's laboratory developed the key things, magnetic trapping, evaporative cooling, that made possible Bose-Einstein condensation by other people, like the laboratory of Eric Cornell and Carl Wyman at the NIST laboratories in Boulder, Wolfgang Ketterle in his laboratory at MIT, very close to Dan Kleppner. Those people used the ideas developed in Kleppner's group in order to achieve Bose-Einstein condensation. So even though the Kleppner and Greytak group were pursuing something that turned out to be not the best way of doing things, they made possible the rest of the community to achieve this marvelous um, new, people have sometimes called a new state of matter, certainly a new kind of phase transition that has revolutionized that part of physics. So today, a great deal of atomic physics is involved with cold quantum degenerate gases, which has come from this work started by Dan Kleppner in 1976. When he asked me to join it, I made almost no progress in the 2 years that I was there. But 22 years later, they achieved it and ended up not doing anything with it because it really wasn't a very good approach, but enabled the rest of the community to do something absolutely marvelous.
That's a fantastic story. And my next question is exactly about the follow-up, which is the foundation of breakthroughs. So perhaps most interesting, albeit unpredictable things are breakthroughs. And one seldom predicts a breakthrough, and they don't know when or if at all it will come. But so the journey towards scientific breakthroughs requires relentless persistence mixed with strategic pivots, I believe. And in your work, at what point do you decide it's time to stop following a particular path and shift directions within the same environment of a given experiment?
Yeah. So that's an excellent question. And again, there are a lot of examples of how that has happened in my own research. So let me tell you one particular story, which I think we'll cycle back in the next question that you're going to ask me about unexpected uh, things. But anyway, and measurement. Uh, we were measuring. Okay, so I should back up and say one of the things that my own laboratory here, my own group here at NIST and at the University of Maryland, within what we call the Joint Quantum Institute, joint between the university and NIST. What we do is make cold atomic gases, and we do it by a very different method from what I described. We started with from that is refrigeration. We use what's called laser cooling. Now, laser cooling is an absolutely crazy idea. Uh, by shining light on things, on a gas of atoms, we make it cold. Now, that sounds pretty crazy because most people know that if you shine light on something, you make it warm. Uh, but in fact, we shine light on things and make it cold. And how that's done is another story, but it works extremely well. And it's the first step that people use today to make Bose condensation. You first make the gas really cold with laser cooling, then you trap it in a magnetic trap, and then you uh, evaporatively cool it and make Bose condensation. Well, at some point, we were measuring the temperature of atoms that were being laser cooled. And Uh, the way we would do that is we would have the laser beams coming in from all directions, cooling this cloud of atoms, and the cooling was so effective that the atoms were, in a sense, we call it viscously confined. That is, the atoms couldn't move very far, maybe just a few micrometers, before the cooling process would damp their velocity so that they were now moving in a different direction. So the motion of the atoms was diffusive, and the atoms would hang around for a long time in this configuration of laser beams coming in from all directions, well, all directions, say the six coordinate directions would be the typical way we would do this. Well, we call this optical molasses because the atoms felt as if they were in a viscous fluid. And that's what kept them hanging around for a long time. And then what would happen would be we would turn off the laser beams, and then the atoms were free to move. They would expand as any gas would expand in a vacuum. And by measuring how far they went in a certain period of time, we could determine what their temperature was. So we were trying to make good measurements of the temperature. Well, uh, 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 we developed a number of different methods for measuring the temperature. Uh, we had some surprises there, and I will talk about that a little bit later. But one of the things that we said, just because we wanted to be careful, we said we were measuring the temperature of atoms released from optical molasses. We never said we were measuring the temperature of atoms in optical molasses because that's not what we were doing. We were measuring the temperature of atoms that were released from the optical molasses. In other words, we had to turn off laser beams. And we realized that that might not be the same as the temperature of the atoms while the laser beams were on. So we thought, well, can we measure the temperature of the atoms when the laser beams are on? So we came up with a scheme for doing that. We would look at the light that was emitted by the atoms when they're being irradiated by the laser. And because of the motion of the atoms, because of the Doppler shift of the emitted light, because the atoms are moving, we could look at those Doppler shifts and determine what the distribution of velocities were. It seemed like a pretty nice technique. So we did that. And we were really surprised at what happened. We found that there was a distribution of velocities along the lines that we expected. And in the middle of that distribution was a big peak that indicated a group of atoms that were hardly moving at all. And we were wondering what is going on. This was not what we expected at all. In fact, for a moment, we thought, did we accidentally produce Bose-Einstein condensation? Because that would have produced a peak of atoms in the middle of a velocity distribution. Uh, and in fact, a few years later, when we did make Bose-Einstein condensation, that's exactly what it looked like. But that wasn't what was going on here. It took us a day or so to realize that what was happening was that the laser beams, the intersection of the laser beams, was creating uh, what we call an interference pattern or a standing wave. And the atoms were actually being trapped in the nodes or antinodes of the standing wave of light. In other words, the interference of the light was producing a kind of a periodic pattern of intensity, and the atoms were being confined because the laser beams exert forces on the atoms, and if you change the intensity of the light, it creates. Imagine a kind of a three-dimensional egg carton and the atoms as being the eggs and being trapped in the places where the egg carton has uh, its little receptacles. That was what was going on with the atoms, and the reason it produced a narrow um, feature on the spectrum was that when you confine atoms to a region of space, or when I say atoms, anything emitting light to a region of space that's smaller than the wavelength of light, then the Doppler shift goes away for part of the light that's being emitted. And this was something that was predicted back in the 1950s by Bob Dickey. It's often called Dickey narrowing. And we were seeing that. And we thought, well, that's lovely. In fact, people had been talking about doing that many years earlier, and now we were finally doing it. And we thought that's wonderful. And at that point, we decided it's time to pivot what we're measuring and what we're concentrating on. We've been concentrating on learning about the temperature. We thought now it's time to concentrate on the behavior of the atoms in this new environment where they're trapped in the standing wave. So we called this standing wave an optical lattice because we're creating a kind of a lattice work of light, and the atoms are being trapped in this lattice. So the atoms are behaving sort of like electrons in a solid that are being trapped or at least influenced by the lattice of atoms and that form uh, the the charged centers in which the electrons move. So if we think about what happens in, say, a conductor or a semiconductor, the atoms are moving in a periodic potential. This is what we learn about in our solid state physics books. And now we had that same kind of situation where the lattice is created not by atoms, but by light. And the thing that's moving through this lattice is not electrons, but atoms. Now, we thought, wow, this is really pretty cool because it's a whole new system that we get to study, but a system that we already know a lot about because we've studied the behavior of electrons in solids for years and years. And so we started a whole new direction of research that we call atoms and optical lattices, and it became quite popular. A few other groups in Europe started doing it, and then everybody was doing it. Uh, and we spent a long time and still are interested in some of the features. So, we thought it was interesting, and it was to study the temperature of atoms being laser cooled. But then we thought it was even more interesting to study this new physical system where we could do different kinds of measurements and uh, uh, different kinds of control of atoms in optical lattices than would ever be possible to measure electrons in solids or to control the behavior of the lattice for a solid state system. And that's been a wonderfully fruitful direction of research.
And speaking of fruitfulness, I think experiments can, back to what you were saying, can be so fruitful that even they outperform predictions. And I want to ask about this in my next question. I don't know how in advance, and it's fair to say that almost nobody knows how in advance, but sometimes experimental results surpass theoretical predictions. Could you share some more about the events where precise measurements led to the results that challenged or even outperformed your expectations? What was that like?
Well, this was probably the event that, in a sense, put our research group on the map. Was we accidentally discovered that laser cooling, this process by which we can reduce the temperature of a gas by shining light on it, that this laser cooling was working better than the theorists had predicted that it could. So the way in which laser cooling works is that you use light to push on atoms because light can exert pressure on things. This is why, at least one of the reasons why the tails of comets point away from the sun because of the pressure of the light. Um, so we use that light pressure to push on atoms in a gas to slow them down. That's the whole idea of laser cooling. And uh, the way it works is you wonder, well, how do you do that? Because when you shine the light in, the atoms are going every which way. It seems like some of them are going to speed up and some of them are going to slow down. And you use the Doppler effect again. So you tune the laser beam so it's a little bit below the resonant frequency of the atoms. So if the atom were at rest, the lasers would not be exciting the atoms at the maximum rate because the frequency of the laser is too low to be resonant with the transitions in the atoms that you want to excite. But if the atom is moving, then the Doppler shift will change the apparent frequency of the laser from in the rest frame of the atom, from the viewpoint of the atom. So if the atom is moving toward the source of the light, that means there's going to be an upshift in the frequency from the point of view of the atoms. But if the frequency was a little bit low, that means for atoms moving toward the laser beam that they're going to be more likely to absorb the light, and that'll make them slow down. But if they're going the other direction, then it's going to look to the atom as if the frequency of the light is too low, and uh, and then they won't absorb very much. So this is the whole idea behind laser cooling, that when the atoms are moving toward the light, they they absorb a lot of light and slow down, and they're moving away from the light, they don't, and then so they don't speed up as so much. And then you bring the laser beams in from all the coordinate directions, and no matter which way the atom goes, it picks out those laser beams that are opposing its motion as being the ones that it most absorbs from. Well, based on that idea, it's not too hard to calculate what the temperature is because there's a balance between the cooling that comes from the process that I've just described and the heating that comes from the fact that the absorption and emission of light, because after the atom absorbs the light, it has to emit it so that it can absorb some more light because it takes many, many photons absorbed by the atoms to cool them down. Well, those processes are random. The emission of the light's random what direction it's going to go in. It's random when it happens. The absorption, it's random which laser beam uh, you're going to absorb from. I mean, you have a preference for absorbing from the ones that slow you down, but it's still random. And that all that randomness heats the atoms up. And you just balance, theoretically, you calculate the balance between the cooling and the heating, and you can figure out what the temperature is. So we knew that. We'd done that calculation, and we expected that the temperature of our atoms, which were sodium atoms, should be no colder than 240 microkelvin. That was the limit that we calculated. And anything that was non-ideal about the experiment should raise the temperature. So we started, we made some initial measurements of the temperature rather roughly. So not a very precise measurement. And we found that it was 240 microkelvin. Now, this was actually after Steve Chu, who you mentioned as sharing the Nobel Prize.
I met him too. He's a wonderful person.
Yes, indeed. And some people may remember that he was the Secretary of Energy during the first Obama administration, the first person, if I'm recalling correctly, uh, who had a Nobel Prize who was appointed to a cabinet position in the United States. Other people, like Henry Kissinger, got a Nobel Prize after they were holding the cabinet position, which he held as Secretary of State. But Steve Chu was the first one who had a Nobel Prize and was then appointed to a cabinet position. A really smart guy, by the way. Anyway, he had also measured this before we had and gotten 240 microkelvin. So this was really, really nice. We were very happy that we had confirmation, two different groups, measuring the temperature and finding it to be as cold as we could get it. And then we started making other measurements to make sure that we understood what was going on. And those other measurements were not consistent with the theory. So we had this situation where a rough measurement of the temperature had produced something consistent with the theory, and other kinds of measurements, measurements about how long it took the atoms to escape from this uh, optical molasses, uh, how that would change when you change the balance of the power, make one of the laser beams more powerful, you'd think it would push the atoms out. We calculated what should happen, and none of those things were behaving the way they should. So we were confused. We had this theory that seemed to give a good explanation of the temperature, although the measurement of the temperature was rough. The reason why the measurement of the temperature was rough was it was really hard to do. And uh, these other measurements were easier to do. So we were doing those and spending more time on those, and they weren't consistent at all with the theory. So finally, we decided, it was one of my colleagues, Paulette, who said, look, why don't we remeasure the temperature? We did a very rough job of measuring the temperature before. Maybe if we measure the temperature more carefully, uh, maybe we'll learn something about what's going on. And so we thought about what can we do to measure the temperature more carefully. So this is important about, making the measurements, making good measurements. I mean, here we are, we're at the National Institute of Standards and Technology. Uh, uh, can't we make better measurements? So we developed an idea for measuring the temperature. And the idea was that we would have the atoms cool them down with these laser beams. Then we would suddenly turn the laser beams off, and we would have another laser beam some distance away from where the atoms were. And when the atoms got to that other laser beam, they would light up, and we could measure how long it took the atoms to get from there, from the original place to this separated place. Um, and from that, we would be able to measure the temperature. So we did that. And uh, the first thing that we did was really confusing to us because we didn't see anything. That is, we didn't see any atoms getting to this other laser beam. Now, the other laser beam was above where the atoms had been, but calculating what the velocity of the atoms would be at the temperature that we'd already measured, the atoms to be. There'd be no problem with the the atoms getting up to where the laser beam was, but we saw nothing. And we did all the checks you need to do to make sure everything's working right. Everything was working fine. And then finally we decided, well, let's put the laser beam under the atoms. Then we got a huge signal. And then we realized, well, it appears that the atoms don't have enough kinetic energy to get up to where the laser beam when it was above, but they're falling down onto the laser beam when it's underneath. And then we made some very careful measurements, and we found that the temperature was not 240 microkelvin, but 40 microkelvin. In other words, 6 times lower than what the theory predicted. Um, and
How did
well,
you feel
so
when that was the case?
worried, we thought we must be making some terrible mistake.
Hmm.
Everybody knew you couldn't get the temperature lower than 240 microkelvin. So what we did was to make sure, well, or to find out what we were doing wrong, we devised 3 additional methods for measuring the temperature. One of them being the one that we'd used the first time, but done more carefully. And the one that it was actually the one that Steve Chu invented. But we thought, let's do it more carefully. There were a lot of real difficulties that we just ignored before, and now we were going to do the hard work to make it a more precise measurement. And then other methods. Like, for example, we thought, well, if that first thing we tried when the laser beam was above the atoms didn't work, well, then we can use that as a way of measuring the temperature. We can change how far above the atoms the laser beam is, and we can use that as a measure of the temperature. So we did all those things. And when they finally all agreed that the temperature was a lot lower than what the theory predicted, then we wrote it up and published it. In addition, we called up our friends in France, the group of Claude Cohen's energy, and told them what we'd seen. They were working on a completely different idea to get to lower temperatures. And their first reaction was maybe we'd accidentally done what they were thinking to do. But then they realized no, nothing like that was going on. Something else was happening. And they calculated what was going on. And then using their calculations, and Steve Chu was also doing calculations, found the same kind of thing. Using those calculations, a new understanding of what was going on, we could make everything work even better because now we knew what was happening, what the physics was behind it. We could make things work even better. And finally, for a different atom, cesium, we were able to get the temperature 200 times lower than what the theory predicted. We got below 1 millionth of a degree for cesium atoms, whereas the temperature said it should be about 140 microkelvin, 140 millionths of a degree. We got it down to zero point 0.7 microdegrees, which
Were
is
you still
about two.
worried then?
Well, by this time we weren't worried because we'd done all these measurements that all agreed. And then it didn't take too long before other people based on our publication, went into their laboratories and did more careful measurements of the temperatures and found agreement with what we had done. So that was that was an incredible experience. And I'm not sure at what point we were experiencing elation about getting these low temperatures and discovering something totally unexpected. From the initial thing of being worried that we were doing something wrong, there was never a eureka moment, which people often think that this is the way science progresses. Um, I think somebody said it's very rarely eureka. Usually it's, now that's strange. And so that was what we were experiencing, that moment of that's strange. What's happening now? And we finally found out what was happening. Uh, and so that's the story of a little bit of how measurement made a difference and completely changed our ideas about what was going on. And that had a really profound effect. Being able to get atoms that cold made it a lot easier to continue with the process toward Bose-Einstein condensation. So that was an important feature in making uh, Bose-Einstein condensation a reality. And other things uh, like atoms and optical lattices. But another thing which is very important is why were we doing this in the first place? And why were we doing it at the National Institute of Standards and Technology? And the answer is we wanted to make better atomic clocks because the limitations in the performance of atomic clocks at that time was because the atoms were moving so fast. And we figured if we can slow the atoms down, then we can do a better job of making atomic clocks. If we hadn't gotten the atoms down to a temperature much lower than predicted by laser cooling, the atomic clock uh, approach that was finally used and is in use today, called atomic fountains, where we take, instead of having a beam of atoms uh, that we use to measure it, instead what we do is we take these laser cooled atoms and toss them up in a vacuum system, and then they come back down. And we use that process to make that measurement. That never would have worked if laser cooling had been limited to the temperatures that was originally thought to be the case. Only because of this accidental discovery was it possible to make these atomic fountains, which today provide timekeeping for the entire world. Most of the industrialized countries of the world have atomic fountains, and they report these results to the International Bureau of Time, and this keeps time for the whole world. And it wouldn't have happened if we hadn't made this accidental discovery because we'd made careful measurements of the temperature and careful measurements of other properties that weren't behaving the way they should. So, another story.
That's fantastic, and it's remarkable, which leads me to believe that there's more questions for me to ask. And my next question is about the equipment exactly. So sometimes the right equipment doesn't exist, compelling scientists to innovate or invent new tools. Can you tell me about an instance when the absence of an adequate equipment directly led to a significant innovation in research, or perhaps one from your career?
Yeah, well, when we first started doing laser cooling, there were not a lot of different kinds of lasers available. The we had to have a laser that we could tune so that we could make the frequency of the laser, the wavelength or color of the laser, be close to the the frequency that the atoms wanted to absorb. Now, the only laser that was available when we first started doing this was a dye laser where you dissolve an organic dye in a solvent, and then you shine uh, a laser on that dye, and then it fluoresces at a different color, and you put that fluorescent medium inside a laser cavity and make a laser. So those dye lasers were just becoming commercially available when I was a graduate student, and I used that technology when I went to NIST to start to do. I went to NIST to do other things, but laser cooling was just a sideline. But anyway, the only atom that we could laser cool using these dye lasers was sodium. Now, we knew that sodium wasn't ideal for doing this because sodium has in its electronic ground state two different hyperfine levels that correspond to different relative orientations of the nuclear and electron spin. And because of the fact that the nucleus has lots of different nuclear um, orientations and these couple to the electron spin. Each one of those um, uh, hyperfine states, as we call them, has a bunch of what we call Zeeman states that are, in the absence of of a magnetic field, degenerate. So they got the same energy, but they correspond to different uh, nuclear and electron spin combinations. Okay, and in sodium, one of the states has three different what we call Zeeman levels. The other one has five different levels, and we realized this made the whole process a little bit more difficult, but we found ways of getting around that. Okay, if we had had any laser we wanted at the time, we probably would have chosen a very different atom, one that didn't have any of this hyperfine structure in the ground state. It would have made life a whole lot easier. Today, we would have chosen something like, say, strontium, which is an alkali earth, that and chosen an isotope of strontium that doesn't have any nuclear spin. And then everything would have been so much easier. Okay? Now, here's the thing. If we had had such a laser at the time, and if we'd chosen something like strontium, we never would have discovered that laser cooling works better than the theory said it should. Because that process of working better, which I didn't describe how that works, depends on the atom having this funny Zeeman structure that we thought was just a complication that made things harder. And it did make things harder, but it also opened up the possibility that the laser cooling worked 200 times better than what it was supposed to. So if we had had better lasers, different, operating at different wavelengths, uh, we would have chosen a different atom and we never would have discovered this wonderful feature that the atoms can be made so much colder. Well, I mean, eventually I think it would have been discovered, but it would have taken a lot longer because people would have concentrated on the easy atoms to laser cool, which are being laser cooled today. In our group, we have uh, laser cooling of strontium in the group of Junyi in the Boulder laboratories. He's making atomic clocks using those strontium atoms that are orders of magnitude better than the best atomic clocks when I first started working at NIST. So those other atoms are doing marvelous things, but there's a lot of important stuff that we wouldn't have discovered if we'd had the right equipment, in quotation marks, the right equipment at the time.
Yeah. And better is always almost relative, right? So
Yes.
better compared to what? And my next question is related to this, I hope and I believe. So Lord Kelvin once famously
Mhm.
said, when you can measure what you're speaking about and express it in numbers, you know something about it. Given your extensive work at the National Institute of Standards and Technology, how does your pursuit of precise measurement change your perception of what truly constitutes scientific understanding?
Yeah. Well, first of all, I think that Kelvin was not necessarily talking about precise measurement, although he certainly understood the concept of of precise of precise measurement. Um, I think that he was talking about measurement in general. I think that he was saying, look, science is about things that you can measure. Sometimes those measurements will be very precise, and sometimes they might only be relatively qualitative, but nevertheless, it's something that you can measure. And this puts it into a different category from other things that might be worth thinking about, but don't involve measurement. For example, let's say the appreciation of literature. This isn't something that you can measure. You can't, um, at least I don't think that there's a way in which you can ascribe a numerical value to how good Shakespeare is compared to, let's say, uh, uh, Victor Hugo. I mean, there's, one's making plays and poetry, the other's writing novels. And even if I mean, could you put a numerical value on Victor Hugo versus Charles Dickens? Both writing novels of very similar sort of things. No, but that doesn't mean it's not important to study. And I think Kelvin understood this very well, and saw this as the thing that distinguished science from other fields of study, which he wasn't trying to denigrate, but that he was trying to make a distinction. And he certainly understood the um, uh, the idea of precision measurement. In fact, he's sometimes quoted, I'm not sure if it's really accurate, uh, around the turn of the century saying, we now understand pretty much everything there is about physics. I'm not sure he really said this. He said that the rest of physics is just going to be adding more decimal points to the measurements that we make on things. We really understand all the basic stuff pretty well. Well, uh, there are other people who, are reported to have said similar things. And of course, they couldn't have been more wrong because at the beginning of the 20th century, we didn't yet understand quantum mechanics. We didn't understand either special or general relativity. And those ideas together completely revolutionized our thinking about physics and really changed our daily lives in ways that were really profound. Um, so in many cases, the things that led to this understanding was measurement. So, for example, what we now call the Planck radiation law. Max Planck in 1900 was trying to attack the problem of what is the spectrum of light emitted by a glowing object that is heated up so that it glows. And we call it black body radiation. And nobody could figure out uh, what it correctly what it was. We had measurements, and people made better measurements after Planck came up with his theory, and those measurements showed that what Planck had proposed was right, and in order for it to work, Planck had to come up with this new idea of a quantum, this idea that energy is exchanged between radiation and matter in chunks that we now call photons. And that was the beginning of quantum mechanics. Uh, and it was because of measurement. You measure the spectrum, you find out that it doesn't fit with your current theories, means you have to have a new theory. And Kelvin thought this is what science is about. You measure things, and by measuring, you really start to understand something fundamental about the way things really are. Whereas other things that you don't measure, well, he says your understanding is kind of vague. And, I think that was a good uh, way of distinguishing the way science works compared to the way literature or uh, philosophy or religion work, things that are worth studying, but aren't the same as science.
And with that said, I want to thank you again for sharing your thoughts and wisdom with us. And it's been a joy and an absolute pleasure talking to you.
It's been a pleasure for me as well. Thank you very much.